All righty, folks. Good to see you all again. We're going to continue on our way as we try to get closer to finishing up our year in calculus. I'm going to throw something at you here. Say I got two functions, y equals x and y equals negative x squared plus 3x. If I take both functions, here, let me see if I can't draw up a couple a little bit here. I just want to kind of look at some things. And let's see here, just for the fun of it, I should probably do one more. There we go. And let's graph this one up here too, just for the fun of it here. Whoop. And when I take a look at these functions here, y equals x, I believe that's going to look kind of somewhat like this function right here. And the y equals negative x squared plus 3x, if I were to draw that one here, it's going to look something kind of like this. Oops, I did that slightly wrong. There we go. Let's see here. Something like that, something like that. And not quite that high. So you can make it a little more realistic. There we go. That's a little bit better. Both these graphs would look like that right there. What if I were to graph both these functions on the same graph? I'm just kind of curious what would happen. So we got 1, 2, 3. I don't need to go too terribly far with this. 1, 2, 3, and 4. So we had the red function to begin with. The linear function y equals x. That would be right about here. And if I were to take the parabola, y equals negative x squared plus 3x, that'd look something kind of like this. I just realized I didn't graph that function quite right. Oh, no, it's all right, I guess. So it'd be like that, be like that. And say I graphed it here. Oh, technically, this line, I need to fix this line. That's the problem right here. This right there should have been right through that. There we go. Now it's a little better. All right, and that graph would have looked like this. If I graph them on the same one, it would look something like that. Now, one of the things that we like to do in calculus is we like to look at the graph and we try to find the area between both curves. Well, how do we make that area show up? Well, if you notice, they're tied in from 0 to 2. And if you can kind of see that where the point of intersections are. They have a point of intersection at 0, 0. And one at 2, 0, or 2, 2. And if we didn't have the graph, we could have still figured out where these two equations intersect. We could have done y taken the two equations, set them equal to each other, and we could have figured out where these two values intersect. We'd have 0 equals negative x squared plus 2x. And if you factor it out, this is by setting these two equations equal to each other, we could have figured out where these two functions, at what x values these two functions had the same. So between x equals 0 and x equals 2. And we did that back in integrated 2, where we took a line and parabola and kind of put them together. So how could I find that area between these two curves? Well, the parabola is on top. So essentially what I'd want to do is, if I were to take this parabola area and I were to subtract or figure out the whole area underneath from 0 to 2. And then if I took the line area from 0 to 2, I could take that parabola, that parabolic area, and subtract the triangle here, and I would have came up with the area under that curve. For instance, I'm just going to outline it so you can see it here. I'm not going to actually go through and figure it out. So here's that triangle area. And here's the parabola area. So if I take that parabola area and subtract that triangle area, I'd find the purple area, which is the area between the two curves. So if I wanted to find that area in between, one way I could do it would have been find the area of the blue underneath the parabola from 0 to 2. That's not the color I wanted. So it'd be from 0 to 2 of negative x squared plus 3x. And I'm going to subtract the area of the red function from 0 to 2. So if I were to subtract the two functions, I would come up with the actual area. Or what we like to do in calculus is we will actually take the two areas and we will put them together. So we'd say, all right, we're going to go from 0 to 2, and we're going to take the big area, so negative x squared plus 3x, and we're going to subtract the smaller area, which is x. By putting them together, we come up with an integral that allows us to figure out how to find that value. So let's go and do that real quick. What would be that area between these two curves? We end up here with negative x squared plus 2x. And we're going to integrate that. That's a 0 there, by the way. So negative 1/3 x cubed plus x squared from 0 to 2. So negative 1/3 times 2 to the third plus 2 squared, and then we're going to subtract the other area. So subtract negative 1/3 times 0 cubed. And from here on out, I'll probably just put that as 0. I wouldn't actually write it all in there. I think you guys at this point in time can do that. And when I calculate, I end up with 4/3. So the area between these two curves is 4/3. Now, what if I didn't have the graph? How could I have figured out which function is the greater function? Easiest way to do that, if I don't have a graph, all you got to do is just try to pick a number between them. So x equals 1. And then from there, plug that number between them into each function to figure out, all right, which one gives me the greater value. So whichever one's the greater value, well, that's the function that would end up coming first. So -1 squared plus 3 times 1. So if you don't have the graphs for them, just pick a value in between those intersection points, and you could actually go through and figure out which one is the greater one, because the greater value is the more positive value, and that'll be the value that goes on top. So if I plug this one in, I get 1. And I can see then that the blue function would have been greater than the red function, so I went blue minus red. Always do the top function minus the bottom function. So this is what we're going to play with today. We're going to figure out the area between two curves, or the area of a bounded region. So let me give you a function. Y equals x plus 2. And y equals x squared minus x minus 1. What I want you guys to do is I want you to figure out what the area would be bounded between these two curves. Go ahead and pause the video and see what you can do. All right, well, let's see what you guys came up with. First of all, I've got to figure out what x values I'm bounding it between. So I'm going to take my two functions, I'm going to set them equal to each other. So 0 equals x squared minus 2x minus 3. So x minus 3, x plus 1. And that means that we're bounded between 3 and -1. All right, so we're going between -1 to 3. Now, which function comes on top? Which function is the greater function? Now, if you don't know, I mean, you can always graph it if you wanted to. I mean, I don't recommend it, but I mean, if you wanted to, you could. So just so you get an idea of what we're looking at anyways, I'm going to go ahead and graph this one so you can at least see it. So if we were to have graphed it, it would have looked something kind of like this. Let's do this. Y-intercept is going this way, and coming back that way. So there's my y equals x plus 2 function. And then the parabola, if I were to plug that one into my graph, let's see here. I would have had a point here at -1 right here. That's going to be at -1 here. 2 would be going, up 2, I believe. Let's see here. 0, -1. 1 would be 1. So that would make this 1. And put this one up here at 5, like that. So the graph would look like this. You can kind of see that the line is bigger than the parabola. Also, this allows you to kind of visualize a little bit about that area we're trying to find. So we're trying to figure out this area between the two curves. But say you didn't graph it. If you didn't graph it, no harm, no foul. Just take a point in between them. Doesn't matter what point. Take any point between our x's here. Say 0. It's kind of an easy one right here. and plug it into both equations to figure out which one gives you the greater y value. So if I plug 0 in for x in the top one in the line, I get 2. If I plug 0 into the parabola, I get 0 squared minus 0 minus 1, which would be a -1. So 2 is greater than -1. Therefore, the parabola would be the value or the equation that would come first. So we're going to do the blue, we're going to do the red line first. So x plus 2. And we're going to subtract x squared minus x minus 1. So we're going to figure out that area between both functions. And we end up with negative x squared plus 2x plus 3 so we get negative 1/3 x cubed plus x squared plus 3x and we're evaluating it from -1 to 3. So plug 3 in there, I get, oh, what's that, a -9 plus 9 plus another 9. And I'm going to subtract 1/3, 1, and -3. And when I figure out that value, I end up with 32/3. All right, let's try another one here, friends. Let's try another one here. What if I give you this time the region bound between y equals the square root of x plus 1, y equals -2x, the y-axis, and x equals 3. So I give you a bunch of values here, a bunch of functions. Let's see if we can't just get an idea of what this graph looks like that we're talking about here. We'll go from there. All right, so I got here one. Oh, that was kind of horrible. Whoop. There we go. 7 and 8. So that y equals the square root of x plus 1. It goes like, would help if I actually put some values here along the y-axis too. I just realized, never did that. Still not the right color. There we go. So we got 1, or 0, 0, 1, 1, 3, 1. So the y equals the square root of x plus 1. It's going to kind of look like this function right here. So I got a nice little curve coming on here. Y equals -2x. We got 0, 0. Looks kind of like this down here. We're heading downward, we're going upward. Something kind of like that. The y-axis, I want to make this just a little bit wider so we can see it here. The y-axis is right here. And x equals 3. That's the line right here. So what we're really being asked here then is, what is this value that's bounded in all these regions in here? And you can kind of see that what two functions were in between the blue and the red function. And we're going from x equals 0 to x equals 3. So those are kind of the bounds. So if I were to graph this here, I'm looking, there's not going to be a way that I can actually set them equal to each other to figure out the bounds. This one I actually had to go with what values they gave me, because remember, the y-axis is really the equation x equals 0. So these right here, those are the bounds, and then I have my two functions. So the square root of x plus 1 minus negative 2x dx. All right, so that's what we're going to play with here. From 0 to 3, x plus 1 to the 1/2 plus 2x dx. So we had 2/3 x plus 1, 3/2 plus x squared from 0 to 3. So plug everything in here, 2/3 times 4 to the 3/2 plus 9. And then we're going to subtract 2/3 times 1 to the 3/2. And we're going to subtract 0. So when I plug all that in there, friends, I end up with a whopping, what's that going to be? 41/3. All right. Let's keep going. Let's see what else we can come up with. Find the area with respect to y. So it means, in other words, towards the y-axis, between y equals x and y equals x squared minus 2. All right, so this is what we're going to play with here. What if I give you something like this? Yeah, but in this case, instead of going towards the x-axis, I ask you to go towards the y-axis. With respect to y means everything needs to be in terms of dx, it needs to be in dy. Okay. Well, you have been doing it everything towards the x-axis, perpendicular to the x-axis, which is why we use dx. Now we're going to be going towards the y-axis, and it's going to be perpendicular to the y-axis. Everything's going to be in terms of dy. So everything pretty much is the exact same. We're going to take these. Oh, I wrote that wrong. Shoot, I just realized I wrote that wrong. Got to do a quick fix. Should be an x. Should have been a y. There you go. So everything's going to be the exact same. It's just instead of doing it to the x-axis and using dx, we're going to be doing it to the y-axis and using dy. So I'm going to set y's equal to y squared minus 2. again, everything is the exact same. It's just instead of solving it for x, I'm solving it for y and doing the same process towards the y-axis. So 0 equals y minus 2, y plus 1. So y equals 2, and y equals negative 1. So we got to pick a value between the two, so we can figure out which value is on top, or which value is the greater value. So I'm going to plug in 0. So which one of my two values is the greater value? If I plug 0 into y equals x, I get y of 0 equals 0. Okay. So the linear one, when x is 0, y is 0. If I plug it into the other one, x of 0 equals 0 squared minus 2, I get negative 2. So in other words, that x equals y, that's my bigger function, and my x equals y squared minus 2 is my lesser function. So this one will go second, and the x equals y, that one will go first. When I go to write my equation, that one will go first. So we're going to go from negative 1 to 2. The greater one goes first, so I have y minus the lesser one, y squared minus 2. There we go. So negative 1, 2. We have negative y squared plus y plus 2. Negative 1/3 y cubed plus 1/2 y squared plus 2y from negative 1 to 2. So we're going to plug in all our values here. Here we go. We get negative 8/3 plus 2 plus 4. So when 2 went in, now we're going to subtract all of our y values. So positive 1/3. We have a positive 1/2. We have a minus 2. And all together, that's going to give us 9/2. So we've been dealing with functions. Hopefully we are feeling pretty decent about those. What about if I make it something a little bit more? Given the domain 0 to 2 pi, find the area bounded between y equals sine x and y equals cosine x. All right, so we're just going to be dealing with the unit circle here. Just so we have an idea of what this looks like here, let's see if we can't think about our graphs here for just a little bit. You know, the range is negative 1 to negative 1 here. We have our 2 pi out here. So sine is literally going to be this. Oops. Here's sine. And here is cosine. So in other words, what I'm asking you folks then is, what is the value from this point right here to this point here? What's the value in between these two curves? All right, we got this. So we take our two functions. I see sine x. So we are going to go back to a little bit of trigonometry here. Going to have to solve a simple trig equation here. And if I divide both sides by cosine, tangent, or sine over cosine would be tangent. So I'm looking for when is tangent of x equal to 1 from 0 to 2 pi. So that'd be at pi over 4 and 5 pi over 4. So we're going to find that area from pi over 4 to 5 pi over 4. So the function that's on top, again, if I don't have it graphed, that's fine. I don't need it. But I am going to have to figure out some value between these two values. So some value between pi over 4, 5 pi over 4. What about pi? Pi is between them. So let's let x be equal to pi. So if I plug pi into both equations, I can figure out which one of these is the greater function. So if I don't have it graphed, so I can't see that sine is, that's okay. I can plug a value that's in between my bounds in, and whichever one gives me the greater value, that is my top function. So sine of pi is sine of pi is 0. Now I need to figure out cosine of pi. So cosine of pi is -1. So 0 is greater than -1. So sine will come first. All right. So we have sine of x minus cosine of x. And we are going to integrate it. So I got to integrate. So sine of x, that'll be negative cosine of x. Again, be very careful. It's very easy to mix up derivatives and integrals for integration. Derivative of cosine would be sine. So minus cosine would be minus sine. And we're going from pi over 4 to 5 pi over 4. All right, so we plug them in here. So negative cosine of 5 pi over 4 minus sine of 5 pi over 4. 5 pi over 4. And I'm going to subtract negative cosine of pi over 4 and negative cosine or minus sine of pi over 4. Now, unlike the rest of these, if they were on the FRQ, I wouldn't have simplified any of the rest of them like I did. But I do have to simplify this one because I have the trig values. Can never leave trig alone. So I do have to simplify this. So cosine of 5 pi over 4 is negative root 2 over 2. So I have a negative root 2 over 2 minus a negative root 2 over 2. Got a lot of negatives coming out here. Minus a negative root 2 over 2. Minus, now on the free response, I could leave my answer like this. unsimplified. But I'm going to assume it's on the multiple choice right now and just take it all the way down to its final answer. So 4 root 2 over 2, which is 2 root 2. All right, let's try one more of these just for the fun of it here. All right, let's find the area bounded between these two functions. Bounded between y equals x cubed plus x squared and y equals negative x squared plus 3x. All right, why don't you guys pause the video here and see if you guys can't figure out what is the area bounded between these two functions. All right, let's see how you did here. So we set them equal to each other. So x cubed plus x squared equals a negative x squared plus 3x. Set it equal to 0 here. X cubed plus 2x squared minus 3x equals 0. And if I factor this, I get x times x plus 3 and x minus 1. Well, this one turns out that I'm going to have 3 times where they cross. So if they cross 3 times, that means I'm going to end up having two different regions. In other words, let's just graph it so we can visualize it again. I want you guys to be able to see this whole thing. Got something like this. The x cubed plus x squared. If I were to graph that, I would have had a graph that looks something kind of like this. I don't need to know everything about it, but it's going to go up, and it's going to come down, and it's going to go up like that. If I take the negative x squared plus 3x, that one's going to look like this. Something kind of like that. And you can see how we would end up with two different shaded regions. We have one right here, and we'd have one right here. Now, knowing that we have two different values, what I'd have to do then is I have to figure out, okay, well, since I have two different regions, I need to know what's the biggest region between -3 and 0. And what's the biggest region between 0 and 1? So I'm looking for, so if I don't have the graph and I can't tell, I can still go through and I'm going to get my values here and I'm going to figure out which one is going to give me the larger values. So if I plug -1 in for this one, I would get 0. If I plug it in for the bottom one here, y of -1, I would end up with -4. So the cubic would have been the greater of the two on the first one, which we can see from the graph anyways. If I take 1/2 and plug it in here, oopsies. Plug 1/2 into the top one here, I get 1/8 and 1/4, which would be 3/8. And if I plug it into the bottom one, I get really not right 1/2 for some reason. There we are. I would have ended up with -1/2 1/2 squared plus 3 times 1/2, which would have been a -1/4, 3/2, 6, that would have been 5/4. And I could see then that the parabola would have been the greater value on the top one. So in the first region, this is my bigger value, and this is my smaller value. So the cubic will go first, the quadratic will go second. But on the second region, the cubic will go second, and the parabola will go first when I write my areas. So I'm going to write this, since I have 2 regions, I'm going to write it as 2 separate integrals. I'm hoping that's what you guys did too when you tried it on your own. So from -3 to 0, I'm going to have the cubic, since that was greater. And then I'm going to subtract the quadratics, because it's second, it had a smaller value. And then we're going to add it from 0 to 1. In this case, on this one, the quadratic had the bigger value. That was the 5/4. And then we're going to subtract the cubic from it. All right, friends. So, got a big giant problem here. Let's see if we can't figure it out. So we're going to be dealing with 2 different problems here. So -3 to 0. And this first one is x cubed plus 2x squared minus 3x. And then we're going to go from 0 to 1 the other way. -x cubed minus 2x squared plus 3x. We integrate both sides here. So 1/4 x to the 4th plus 2/3 x cubed minus 3/2 x squared. Not really sure why I put that one in parentheses. Oh well. And then that's going to go from 0 to -3. And we're going to add to it the exact opposite. Some people like to put it in absolute value and go from -3 to 1. That would have worked as well. But if we're on the non-calculator portion of the test, well, that's not going to work out so hot. All right, so put in the first number. So 0 minus 81/4. Plug that in there. I'm going to get, there you go, minus 18 minus 27/2 plus -1/4 minus 2/3 plus 3/2 minus 0. And when I plug in the whole thing, I end up with 71/6. All right, friends, so we have the area between 2 curves. Really, it's just kind of a continuation of things we've done before, nothing too terribly new. So give it a shot, and we will talk more about it when we come back to school. All right, see you guys later.